Hey everybody, welcome back. Mr. Smith here. In the last slide deck, what we did was we laid down the rules of Kirchoff's laws, and we took a look at a pretty simple example. What we're going to do is to take a look at a little bit more complicated example right now and show you how those same laws apply, but we're going to use this as a bridge to some more sophisticated math, which becomes not necessary, but it becomes really handy to have when you're dealing with more complicated examples. So what we're going to do is start with something that looks a lot hairier than the last example we did. Let me grab my pen tool here. And we're still going to employ the same tactics. The rule number one was conservation of charge, that if 5 amps of current went into point A and 2 amps went upwards, then that meant that 3 amps had to be going downwards. Rule number two said that on any closed loop, the sum of all the voltage changes always had to add up to equal 0. And so what we're going to do is just go ahead and use those along with our 3 strategies. Now you remember that the first strategy I like to do means that I get a little annoyed when I see the textbooks being so helpful in telling me the directions of the current. I left this alone, this example from our textbook, because I actually agreed with the directions that they chose. But I want to go through the first step anyway, because I think it's really helpful. There's actually a reason to do it. Again, what I'm looking for is to make sure that as I work my way through and I think about how I believe this is going to work, that I don't create conflicts on any shared parts of the circuit. So what do I always do? Start on an 80 volt battery. Why? It's the nearest one to me. So charges are going to come out of the 80 volts, work their way through here. They're going to come up to the first connection or junction, and I'm going to take a left turn at letter D, and I'm going to keep on cruising and go this way. And so if I did that make sense? Well, 80 volts was pushing to the right. When I hit letter D, I got a 45 volt push into the left direction. And so, yeah, I think that actually made a lot of sense to me that this lower loop works counterclockwise. Okay, so we'll call that loop 2, actually. And we'll go and take a look at this upper one, and we'll use the upper loop as loop 1. To analyze loop 1, start at any battery. We'll only have one. So I've got 45 volts, and he's going to push this way. And I feel good about that because I agree that the direction on loop 2 of the current in this middle leg is to the left. When I think about the upper loop, it also looks to me like the direction on that shared middle leg is to the left. So that checks out and I feel good about it. So what I'm going to do is just go ahead and traipse from 45 through the 1 ohm through the 40 ohm, and I don't see anything that's going to convince me that I'm wrong as I trace that loop. So what did I do? I gave myself enough insight to feel confident moving on to the next step, where I'm going to use the junction or the node rule to go ahead and lay down our first equation. So what I've got here is it looks to me like I3 comes in this direction, and then I2 comes out of that direction. Excuse me, I1 is the top one, and then I2 is this one down here, and it looks like so. And this, I believe, is the same equation we ended up with in the last example. We had I3 coming in, equaling the sum of I1 plus I2, and it's as simple as that. So node equation is done. What I'm going to do now, since I have 3 possible loops here, upper, lower, and outer, I'm going to make 2 loop equations so that I'll end up with a system of equations of 3 equations and 3 unknowns. So upper one first. Let's go ahead and start with the 45. Charge gets a little bump from the 45 volt battery. The next thing it does is it loses energy. So this next step is a minus 1 I3. Here's a minus 40 I3. I could combine those because I know that the 1 and the 40 are in series, and I might do that just to save a little space. So 40 minus 41 I3s is the next energy change for my charge. Then I hit point A, bump up to the right, take another right turn, and I go through the 30 ohm resistor. Now I'm in I1 territory, so the energy loss is minus 30 ohms times I1 amps is that many volts. And I come back on down to the other side of the battery, and that's where the loop ends, and all of those changes add up to equal 0. Now I can write this a little more neatly and have it have a little bit better manners as an equation. So if I write minus 30 I1s, I don't have any I2s, minus 41 I3s plus 45 equals 0. Okay, that's fine as far as it goes. But what I'm going to want to do later is actually nudge these numbers over to the other side. And if I do it, it becomes a minus 45. And then I realize all my terms are actually minus. So in algebra, it's fine to multiply a whole equation by -1 as long as you do it on both sides. So if I rewrite this one as 30I1 plus 41I3s equals 45, that should all check out too. Okay, so that's just a different way to write it. So let's go and get the lower equation and check that one out. So lower equation, I'm going to start at the 80-volt battery. So my first move is plus 80. A charge goes through a 1 ohm resistor and a 20 ohm resistor. Now I'm down in I2 territory. So I'm going to lump those together. Minus 21 I2 volts. Hit letter D, cruise to the left. I get an energy bump, plus 45. I hit these shared resistors again. Now I'm in I3 territory. We just did this term a second ago, minus 41 I3s. And we cruise back on down to the battery. We're done. So the closed loop always adds up to equal 0. Now I'm going to do a little cleaning up on this one. We've got minus 21 I2s, minus 41 I3s, and I go plus 125 when I add up the 45 and the 80. That all adds up to equal 0. And I think I see the exact same thing happening with minus signs that happened in the last step. I can shift the 125 over and rewrite this whole thing after I multiply it all by -1 as 21 I2s plus 41 I3s and then equals 125. Okay, so what I want to show you in the next step is I'm going to summarize the equations. And in real life, with all these problems, sometimes the problems in the textbook especially are so easy, you really don't need to use a hammer like the matrix solution system I'm going to show you. Sometimes they're easier and you can use a little quick substitution, and I1 will equal 2 times I2 or something like that, and you can simplify the equation using tactics that are common in math class. But Kirchoff's laws are really done in the real world of electrical engineering using matrices. And the reason is that matrices are so strong that they can handle differential equations, and they're tracking a thing that's changing over time, and there's calculus, and there's a whole lot going on besides what I'm showing you here. So it's a really good technique, and it always works no matter what. So the key to setting things up to work in a matrix is that you have to be organized. So what you're going to see me do is push my equations around a little bit more neatly and get them set up so that they're in form. So what I'm going to do is take my first node equation. I'm going to always rewrite these as number times I1 plus number times I2 plus number times I3 equals some number. So what I'm going to do is pretty simple for this first one. I1 plus I2 minus I3 equals 0. So fair enough. I just went ahead and shifted the I3 over to the same side, and I'm left with 0 on the right. Okay, I'm going to do something very similar here, which is just to leave a space now. This is going to become 30 I1s plus 0 I2s plus 41 I3s, and that's going to equal 45. And lastly, I'm going to have 0 I1s plus 21 I2s, plus 41 I3s equals 125. Okay? And the reason for this you'll see in just a second. So I have I1, I2, and I3 are all in one column. I have the coefficients of the i's all organized according to the system that I just showed you, and those are always equal to some number. So the upshot of the way this is organized is I have here matrix A, I have matrix I, and I have matrix B. And what you're going to see me do is plug in the actual numbers that we had, and we're going to go through an operation in the next video that's pretty concise, where we're going to solve for matrix I by inverting all of these numbers right here in matrix form, multiplying them into matrix B, and solving for our current. What I've done here is taken our equations, organized them now into matrix A, matrix I, and matrix B, And what we're going to do is go through the process in the next little video of inverting matrix A into matrix B and solving for I. Okay, so check that one out. Bring your questions to class if you have any. Good to see you. Thanks for watching, and take care. Bye-bye.